Okay, let's try it. Let's try to derive the Michaelis-Menten equation. So we're starting with the thought that this equation describes the velocity. However, it has a concentration of something we can't measure. We can't measure that. We don't know how much is free enzyme. We do know how much is our total enzyme. We do know how much substrate's in there. And so let's try to figure out a way to do this. Now, what we're going to do at the start of this is to try to use this concept that the concentration of the enzyme-substrate complex reaches equilibrium. And again, we know that equilibrium is this dynamic situation where the enzyme-substrate complex is being formed and it's being dissolved, and the rates of those two things are equal at equilibrium. So, in order to describe this equilibrium mathematically, we can say that the rate of formation of the enzyme-substrate complex equals the rate of, dissociation. Dissociation. That'll work. So, how is the enzyme substrate formed? Well, there's only one way to make it. Enzyme plus substrate, according to this rate constant, makes enzyme substrate complex. So the rate at which it's formed is equal to K1 times the concentration of the enzyme times the concentration of the substrate. Sort of a second order reaction. That's the only way, according to this, we can make it. Now, how can we get rid of it? Well, one way is that it just dissociates back to free enzyme and substrate. That's governed by the K-1 rate constant and is dependent on the concentration of the enzyme substrate complex, since we're really thinking about this backward reaction. Now there's another way in which we can dissociate that, and that's for it to make product. And that's governed by K2, again, times concentration of enzyme substrate complex. Okay, so we've got an equation here. Well, how is this useful? Well, the plan is, remember, we were going to try to use this equation, except substitute something in here for enzyme substrate complex that we can measure. So it may be if we sort of get these enzyme substrate complexes to one side of the equation, it'll equal to something that we can substitute in here. So let's try to do that. Okay, so how are we going to do this? I hate this. Free enzyme. I don't know what that is. This is okay because I'm going to get this to one side of the equation. So let's substitute in, something for the free enzyme. That makes a little more sense. So let's do K1 times concentration of substrate times something else. Instead of free enzyme, let's just say that free enzyme is equal to the total enzyme minus enzyme substrate complex. I like total enzyme because I know how much total enzyme I'm adding to my reaction, and I can tolerate the enzyme substrate complex as long as I can eventually get it together with those and the other side of the equation. Okay, let's look at that for a minute. Now, we got to get all these enzyme substrate complexes to the same side of the equation, and let's try to get all of our K values to the same side of the equation also. Why don't we divide everything by, let's say, K1 times enzyme substrate complex. Let's see if that simplifies things. Okay. So if I divide the left side of this equation by that, I'll get, let's see, if I multiply that whole thing out, right, I'll get concentration of total enzyme times concentration of substrate over enzyme substrate complex. That's this divided by that. And then if I have this divided by that, I'm going to get minus concentration of just substrate. That is yucky. I don't like that, but let's stick with it for now. What happens when we go to this side of the equation and divide it by K1? Yes. Well, I get a bunch of rate constants together. My ES has disappeared, and I'm left with a bunch of rate constants. Now, that actually accomplished something, believe it or not. Instead of having 3 places where my enzyme substrate complex is, it's just here. So the rest of this, I'm just going to try to get this enzyme substrate complex by itself, have it equal to something, and then substitute that something right in there. Now this is gross, right? This is a bunch of rate constants together. And since they're all constants, we can just make a new constant here that describes these things. And this is actually equal to a famous rate constant called the Michaelis constant, or Km. Km equals all these constants together, right? And we're going to think a little more deeply about what Km means in a minute. But we can just say, instead of having all these constants, let's just make a new constant, call it Km. Okay, so let's try to get ES by itself so we can substitute it in there. So let's say we've got concentration of ES over, whoops, let me erase that. Mess that up. Let's have concentration of ET times concentration of S over concentration of ES equals Km. And then I'll move this substrate over to the other side, plus concentration of substrate. Now, if I try to get enzyme substrate complex by itself, it's pretty easy, right? It's going to be equal to what? Concentration of total enzyme times concentration of substrate over Km plus concentration of substrate. Okay, this is great, actually, right? We've got the concentration of something we hated in the first place because we couldn't measure it, and we've put it into form where we can measure stuff. We know the total enzyme concentration, we know the substrate concentration, so let's substitute this whole thing in over here. And we can, I'll use a different colored marker because they're available. Velocity equals K2 times all this stuff, right? Concentration of total enzyme, concentration of substrate over Km plus concentration of substrate. Okay. Hopefully your gut sort of flipped when I did that, because we spent effort trying to get rid of these ugly constants, replacing it with something else, and now we've added another K2 to it. Which seems pointless, right? And ruined the work that we did over here. But what we can do is, if you notice, K2 times the total enzyme concentration is equal to Vmax. So that's sort of conceptually a nice thing to think about. I can think about how fast can this reaction go? What's its maximal velocity? And so let's substitute Vmax in for K2 times the enzyme, total enzyme concentration. Vmax times concentration of substrate over Km plus concentration of substrate. Boom, we did it, right? I'm going to get an orange marker to celebrate our accomplishment, right? That's not orange. This is the Michaelis-Menten equation, right? Which was named after Michaelis and Menten, right? For doing this, right? Just a derivation with some assumptions and a nice equation that describes enzyme-catalyzed reaction. And it's super important to biochemistry. It's been used for years and years and years by enzyme kineticists in order to predict the rate of an enzyme-catalyzed reaction, just knowing the Vmax and the substrate concentration and the Km. Now, you still should be pretty unsatisfied with what Km is. Vmax makes a little bit of sense. You know what the concentration of substrate means. Km just seems like a jumble of rate constants, and it is, right? But it has some value associated with it that we will talk about in the next video.